In this video, we will learn how to find out the elasticity of substitution of a constant elasticity substitution production function. The question is, given the CES production function is y is equal to x1 raised power theta plus x2 raised power theta whole raised power 1 upon theta, we need to find out the elasticity of substitution. Okay, so what we are being given, and let us write it here. We are being given y denotes the output, and it is the function of two inputs x1 and x2 here. So we have x1 raised power theta plus x2 raised power theta. Okay, x1 and x2 denote the two inputs used in the production process, and this theta denotes this what we call this theta as the substitution parameter, which is used to determine the elasticity of substitution. Okay, now how do we calculate? And let's find it here. By elasticity of substitution, what we mean? So let me write it here. Elasticity of substitution so let's denote it by del here. Okay, so the elasticity of substitution actually measures how the input ratio changes relative to the change in the marginal rate of technical substitution between the inputs. Okay, if we have capital and labor as the inputs, here it is not being defined x1 and x2. Let's assume we have the capital and labor here. Then elasticity of substitution will measure how the capital labor ratio changes relative to the change in the marginal rate of technical substitution between labor and capital. And it is being given, elasticity of substitution is being given as is. The formula is pretty simple. That is the change in the capital labor ratio, or we don't have here capital labor ratio. And let me explain how we will calculate. First thing is, we need to find out the marginal rate of technical substitution, and let's write it here. Marginal rate of technical substitution between capital and labor, or labor and capital, is being given. We know that the MRTS is being given by the marginal product. Sorry, we don't have labor and capital here. We have inputs 1 and 2. Let's write here 1, 2. It will be given us by the marginal product of input 1 upon marginal product of input 2. Okay, that implies we first need to calculate these MP1 and MP2. So MP1 means the partial derivative of the given production function with respect to input 1, that is del x1. So given this production function, we need to differentiate it partially with respect to x1. So what will happen here? First we apply the power function rule. 1 upon theta will become coefficient, so we have 1 upon theta. Okay, then we have x1 raised power theta plus x2 raised power theta, and exponent is subtracted by 1, so we have 1 upon theta minus 1. Okay, so we apply the power function rule, then we multiply, that is we use the chain rule, that is the derivative of whatever is in the brackets with respect to x1 of this x1 theta plus x2 theta. Simple thing, we are applying the chain rule here. So first we use the power function rule, and then we differentiate again with respect to x1. So what will we get here? Let us see. So we have 1 upon theta, then let me see if I have, yes, I have this color, x1 theta plus x2 theta. So we have 1 minus theta upon theta, 1 minus theta upon theta. And what is the derivative of this function with respect to x1? So derivative of x1 raised power theta will be equal to, theta will become coefficient, then we have x1, and exponent is subtracted by 1, theta minus 1, and the derivative of x2 will be 0 because we are taking the partials with respect to x1 here. So this theta and theta gets cancelled. We are left with x1 raised power theta plus x2 raised power theta. Then we have raised power 1 minus theta upon theta, and we have x1 raised power theta minus 1. Okay, similarly we need to find out the marginal product of good 2. Marginal product of input 2, that is simply the partial derivative of production function with respect to input x2. Symmetrically, using this very stuff, what will we get? We partially differentiate this function with respect to x2 this time. Again, applying first the power function rule, 1 upon theta will, this 1 upon theta will become coefficient. Then we have x1 theta plus x2 theta. Okay, I will skip one step here, okay, to save the space. Then we use so when we solve this, 1 upon theta minus 1, it will become 1 minus theta divided by theta, and then we internally differentiate with respect to x2 again. Okay, that is applying chain rule. So the derivative of x2 theta will be, theta will become coefficient, x2 and exponent will be subtracted by 1. Okay, simple thing. I am just skipping one simple step here, you can see here. So this theta gets cancelled. That means MP, marginal product of input 2, will be equal to x1 theta plus x2 theta. Okay, in fact it was not theta, it was what we call the rho symbol here. I was not able to write it properly, so I have used theta in place of this rho. So we have 1 minus theta upon theta. Then we have x2 raised power theta minus 1. Now we know that at optimum, what we do, we equate, that means first order condition for optimization requires what we also call the tangency condition, that our marginal rate of technical substitution between good 1 and 2 should be equal to the ratio of the input prices. Let's denote P1. Okay, what we are doing here, so we are just equating the marginal rate of technical substitution with so our marginal rate of technical substitution is the ratio of MP1 upon MP2. So I can write it here, MRTS between input 1 and 2 is equal to marginal product of input 1, which we got here, and this very function, that is x1 theta plus x2 raised power theta whole 1 minus theta upon theta, x1 raised power theta minus 1. To this we divide by MP2, and MP2 is this very function, x1 theta plus x2 theta whole raised power 1 minus theta upon theta into x2 theta minus 1. Okay, so here this term and this term, these are same, we can cancel them. So we are left with x1 raised power theta minus 1 divided by x2 raised power theta minus 1. So we can write it as MRTS between good input 1 and 2 is equal to, can I rewrite it in this fashion, x1 upon x2 raised power theta minus 1, and can I rewrite it in this fashion, that is x2 upon x1 whole raised power 1 minus theta. Simply I am reciprocating numerator with denominator, and you can check it out easily. It will become 1 minus theta. Now what is the elasticity of substitution? Elasticity of substitution, let's denote it by delta. This very symbol, it is being given by the change in the input ratio, that is x2 upon x1, divided by the change in the marginal rate of technical substitution into marginal rate of technical substitution upon the change in the input ratio x2 upon x1. Okay, the way we calculate the elasticity of demand, same applies here. Okay, so let us rewrite this MRTS again here to make sense. So MRTS is equal to this very stuff. Let me see if I have the space to show it here. So our MRTS is equal to x2 upon x1 raised power 1 minus theta. So transposing this here, it will become, so x2 upon x1 will become MRTS. Transposing this here, this exponent, it will get reciprocated, it will become exponent but in reciprocal order. So we have 1 minus theta here. Okay, so we have this very function. So the change in the input, the change in the input ratio due to the change in the marginal rate of technical substitution, that means we need to differentiate this function with respect to MRTS. So what will we get here? And let me write it here. So the change in the input ratio, that is x2 upon x1 divided by the change in MRTS. So we differentiate this function with respect to MRTS. So the derivative of MRTS raised power 1 upon 1 minus theta. So 1 upon 1 minus theta, 1 upon 1 minus theta will become coefficient by power function rule. Then we have MRTS and 1 divided by 1 minus theta, and it will be subtracted by 1. So we will get, if we solve this, 1 divided by 1 minus theta minus 1. So what will it become? So I'm just trying to first solve this very stuff. So we have 1 minus, then we have 1 minus theta divided by 1 minus theta. So it will become 1 minus 1 plus theta divided by 1 minus theta. Okay, so we will get theta divided by 1 minus theta as the exponent here. So let me rub this out. So when we solve this, and let me see if I have the space left here. I have to be very cautious here to see the space available. So elasticity of substitution, we got this very stuff, that is equal to 1 divided by 1 minus theta MRTS, and this stuff came out, I forgot it instantaneously. So we have 1 minus, then we have 1 minus theta divided by 1 minus theta. So it becomes 1 minus 1 plus theta divided by 1 minus theta. So we got as theta divided by 1 minus theta. So elasticity of substitution, so this very derivative came out to be this very stuff. To this we multiply MRTS, that is MRTS, and we divide by x2 upon x1. Let us see what is x2 upon x1. X2 upon x1 is this very stuff. So let us write MRTS as raised power 1 divided by 1 minus theta in this place. So solving this, bases are same in the numerator. What will we get? So we have MRTS, so we can add the exponents here. We have theta divided by 1 minus theta, then we have plus 1 here, Okay, then, and let us see what it comes out to be. It comes out to be theta plus 1 minus theta. Theta gets cancelled, so we will get 1 divided by 1 minus theta. Okay, so when we multiply the bases here, okay, I fear that I lost the space. So we will get here, when we solve this, when we add these two things, we will get 1 divided by 1 minus theta first. This very stuff, you know, bases are same when we add the exponents. So we will get here m or ts raised power 1 divided by 1 minus theta, okay, which we calculated, divided by m or ts 1 divided by 1 minus theta. So here these two terms gets cancelled, and we get the elasticity of substitution equal to 1 divided by 1 minus theta, which is constant here. It depends upon this theta, which is the substitution parameter. Okay, I hope I make myself clear in this video. Thank you.